This time we're looking at semiconductors and doping. The example semiconductor we've been using is silicon. And silicon has a Fermi level here, which is in between a full valence band and an empty conduction band in the ground state. However, the top of the valence band and the bottom of the conduction band are not very far apart, which means that at most temperatures, the probability is that there will be a few electrons in the conduction band and there will be a few empty orbits or holes at the top of the valence band. And that does allow a small amount of current to pass. However, this does result in a resistance which is a strong function of temperature, because as the temperature increases and the Fermi-Dirac distribution predicts there will be more electrons in the conduction band and more available states in the valence band, the resistivity of the medium goes down. This is not a particularly useful property of an electronic material, when you want the properties to be reasonably stable with temperature in most cases. One thing you can do about this, which helps stabilize the properties of the semiconductor with temperature, is something called doping. Doping is introducing controlled amounts of impurities into the semiconductor in order to change its properties. In the case of silicon, note that aluminium at location 13 in the periodic table has one fewer electron than silicon, and phosphorus at location 15 has one more electron than a silicon atom. If you don't put many of these impurity atoms in your lattice, then the structure of the lattice is not particularly affected, since these electrons in the outer shells tend to be smeared out around several atoms anyway in terms of their orbits. All that does happen if you put an aluminium atom into a load of silicon is that there is one fewer electrons to fill up these orbits, these outer orbits. Conversely, putting an atom of phosphorus into your lattice introduces an additional electron into your lattice. Removing an electron produces what's known as a P-type semiconductor. Adding an extra electron produces what is known as an N-type semiconductor. In terms of the energy levels, this is what's happening. With an N-type semiconductor with additional electrons in, some of these states at the bottom of the conduction band have to be full, because there isn't room in the valence band for them. Practically all of the valence bands are full. These extra electrons introduced by the phosphorus atoms have to go in the bottom of the conduction band. That effectively moves the average energy of these electrons higher, pushing the Fermi level up to this point here, just below the conduction band. Conversely, using aluminium impurity and thereby removing an electron pushes the Fermi level down as it forces there to be some vacant states at the top of the valence band. So now we have a situation where the conduction band is almost entirely empty, but there are more states available unfilled at the top of the valence band. With N-type, since most of these electrons in the conduction band, which is what carries the current, they are there due to the impurities and not due to the effects of temperature. And the same thing is true of the gaps, the unfilled state in the valence band. That means that the conductivity of the material is a much less strong function of temperature and can be much better controlled. This is a good thing. An undoped, or sometimes called an intrinsic semiconductor, looks like this. If I put a slight field on it, then we can get current flowing, just not that much current, because there aren't many electrons in the conduction band to carry it, and there aren't many of these holes in the valence band that the electrons can move into. A block of N-type semiconductor has more electrons available in the conduction band, although the valence band is completely full, but it can still conduct quite a good amount of current just from the electrons in the conduction band. And a P-type semiconductor can conduct electricity just by all these electrons moving in the valence band. Due to the fact that in the valence band the electrons have to wait for the next state to be available before they can move, P-type semiconductors tend to have a higher resistance than N-type semiconductors. Next time we'll look at something fascinating that happens when you take a block of P-type semiconductor and a block of N-type semiconductor and put them together. The so-called p-n junction.